In thinking about viruses, we are repeatedly impressed that something so simple can be so smart. Basically, the key to this riddle is molecular or evolutionary intelligence. It's like you had this little computer program endowed with the ability to replicate, but it doesn't do it perfectly every time. If some of the programs become better at replicating, they will take over, and pretty soon you won't see the original program at all. You'll see the modified program. From there, they can modify it further, and as they make each of these modifications, they get better and better at reproducing. It looks like they have a strategy, but what they're really doing is just selecting for the variants that are most effective at carrying out the mandate of replication. Could you use viruses as a supercomputer to explore the information space of cell entry and other biological mechanisms, just like we use artificial intelligence for drug discovery? Absolutely. This reminds me a bit of what we're trying to do with phage therapy. If you have a phage candidate that you want to use to target a bacterial pathogen, is it a problem if different people have that bacterial pathogen with a different genotype? Is my phage going to work the same in them as it works in you? We are trying to use our huge experiments that look at different phage and different genotypes of the target pathogen in order to create a big grid of infection success, or not, for a particular phage. This is accomplished by creating a more variable phage population to examine the possibilities. I took a microbiology course and was introduced to the bacteriophage lambda, which was the first virus I ever really knew anything about. I was so impressed by how clever it was, just this little packet of genes in a protein coat, that I decided to change my career and become a virologist. I did my PhD in human virology, working on hepatitis B virus. I didn't really want to stay in animal or human research because I felt like plants offered an area where you could do a lot more work. For example, you can have 1,000 genetically identical hosts to work with, and they're inexpensive, and no one minds when you put them in the blender either. This book dealt with complicated protein structures and crystals, and contained images. One of the images my professor put up at the time was a crystalline array of an RNA virus in the cytoplasm of an infected cell. At the time, I was very intrigued by the interface between life and chemistry, seeing the image of that crystal, in a sense, crystallized in my mind, that viruses were at that junction. They were the interface between life and chemistry. They were chemical entities, yet they had all these characteristics of life. Molecular systems. He has over 15 years of experience in next-generation sequencing, multiomics, and computational biology. He's been here from the beginning to make sure everything's running smoothly. Right now, he and his team are focusing on developing diagnostics and biotherapies to combat COVID-19, as well as repurposing bacteriophage or bacterial viruses to tackle multi-drug resistance. Of information within their DNA. A bacterium is typically 3 or 4 megabytes, and the human genome is about 4 gigabytes. All of that is written in a biological code, so to speak, and as human beings, we have been learning to decode it since the first genome started coming out in the early 1990s. There is so much information in biology once you start sequencing DNA. Philosophy of Sciences, where since 2012, she is the director of the Applied Evolutionary Epistemology Lab that was founded with the support of the John Templeton Foundation. She has a background in both philosophy and comparative science of cultures, cultural anthropology, and she holds a PhD in philosophy of science. She is the editor-in-chief of the Springer Nature book series, Interdisciplinary Evolution Research, associate editor for evolutionary biology, advisory editorial board member for Theoria et Historia Scientiarum, and review editor for Frontiers in Psychology, Theoretical and Philosophical Psychology. She sits on the permanent board of the Proto-Lang Conference series. She is a member of the Third Way of Evolution and a collaborator for the Astro. We are taping this conversation in the middle of a coronavirus pandemic, and it just so happens that I've been working on coronaviruses since around 2004, when I started my postdoc at the University of North Carolina in Chapel Hill. I started working on SARS-1, working on pathogenesis, host factors, and viral proteins that affect disease. Then I started at the University of Maryland School of Medicine in Baltimore. In 2009, I started my own lab, still working on SARS. In 2012, we worked on MERS coronavirus. We are merging that work into SARS-CoV-2 and trying to study all aspects of therapeutic design, pathogenesis, how the virus works, and how the disease replicates. We are really trying to understand. That brings us to the end of the Finding Genius book, Understanding Viruses by Richard Jacobs. It was read for you by Brian J. Ford, and I can only hope that you learned as much from it as did I. Goodbye.